Hi everyone, I'm Dandika Vignesh. We are from VNIT Nagpur. So this video is regarding differential scanning calorimetry. So what is differential scanning calorimetry? DSC, it is a thermoanalytical technique. It is used for thermal analysis. So when I say thermal analysis, you might be having a doubt like what is thermal analysis? So before we go into our topic DSC, we will be first going into thermal analysis. So let us understand what is thermal analysis. So, thermal analysis. Thermal analysis, it is a branch of material science where the properties of material they are studied with change in temperature. So, this is usually done in a controlled temperature program where physical properties and chemical properties changes are monitored as a function of temperature. This thermal analysis technique is also used in polymers, in inorganic compounds, alloys, drugs, and other organic materials. So, coming to the different techniques of thermal analysis. Thermal analysis, it basically consists of 5 techniques. Differential thermal analysis, DTA, differential scanning calorimetry, DSC, thermogravimetric analysis, TGA, dynamic mechanical analysis, DMA, thermo-optical analysis, TOA. So, in DTA, we are finding out the temperature difference, whereas in DSC we are finding out enthalpy. In similar manner, in TGA mass, and in DMA deformation, and TOA optical properties. So these are different types of techniques for thermal analysis. Now coming to our topic, what is DSC? DSC, it is nothing but differential scanning calorimetry. So calorimetry, it is a combination of two words, calor and metron. Calor, whose meaning is heat, and metron, whose meaning is measure. So, a calorimeter is the one which measures how much heat is flowing into or out of the sample. And what is differential calorimeter? It is nothing but the thing, it also measures the heat, but it is related to a reference material. And what is differential scanning calorimeter? It is the one which does all the above and heats the sample with a linear temperature range. Now, coming to the history. This technique was developed by E.S. Watson and M.J. O'Neill in 1962, and it was industrially introduced at 1963 Pittsburgh Conference on Analytical Chemistry and Applied Spectroscopy. The first adiabatic differential scanning calorimeter that could be used in biochemistry. It was developed by P.L. Privalov and D.R. Monocelast in 1964 at Institute of Physics in Georgia. Now, coming to the introduction part of our equipment, DSC. As I have mentioned it earlier, DSC, it is a thermoanalytical technique which is used to investigate how material responds to heat. Calorimetry, it is a technique like how much heat is absorbed or released by a sample when it undergoes a physical or chemical change. And as we know from first law of thermodynamics, at constant pressure, the dq, which is also known as dH. So here we are interested in finding out the change in enthalpy between the two states. So as we know that del H, which is nothing but change in enthalpy, it is equal to integral Cp dot dt, where Cp is nothing but specific heat capacity. So this, to find out del H, we need to find out the value of Cp, which is a function of temperature. So here we will be using the quantity of heat per unit time to find out the value of Cp from the expression Q dot by M is equal to V dot Cp, where V, which is nothing but a proportionality constant, it is nothing but the heating rate. Now, what can DSC measure? DSC can measure glass transition temperatures, melting and boiling points, crystallization temperatures, percentage of crystallinity, heat of fusions and reactions, specific heat, oxidative and thermal stability, rate and degree of cure, and reaction kinetics. These all can be measured using differential scanning calorimetry. Now, coming to the working principle of DSC. Here the main working principle is nothing but like how much energy is necessary to to establish a zero temperature difference between sample and reference material, it is recorded as a function of temperature or time. So when these both sample and reference material are heated or cooled at a predetermined rate, our intention is to maintain a zero temperature difference between sample and reference material. So like when a transition occurs, like when an endothermic transition occurs, the energy is absorbed by the sample. So to compensate whatever the energy absorbed by the sample, we would be inputting more energy to the sample in order to maintain a zero temperature difference. So this, how much we are inputting the energy, like this amount, it is equivalent in magnitude to the energy absorbed in the transition. So in this manner, we would be finding out whatever the change in enthalpy value we would be getting during the particular transition. Now, measuring principle. Two major methods of DSC are available. Like DSC can be operated in two methods. One is heat flux and the other is power compensation method. In heat flux method, the temperature difference between sample and reference, it is recorded as a direct measure of difference in heat flow rate. And whereas in power compensation method, the difference in power supplied to the sample and to the reference, this difference, because of this difference, there will be temperature difference around the sample and reference. So we would be inputting power sufficient so that to have a zero temperature difference between the sample and reference. In this manner, power compensation DSC works. And here is a pictorial representation of our DSC, where reference, sample and heater are shown here. Now, coming to heat flux DSC, the pictorial representation is shown towards the right side, where sample and reference both are placed in the same furnace. So here, the heat flux, like whatever the heat flux is maintained constant. Like we are maintaining a constant. We are maintaining a linear function of temperature here. Like both specimen and reference material, they are cooled or heated together in a controlled temperature program. And what are the advantages of this mode? The advantage of this mode is that it is easy to handle and relative robustness. Like it can, whatever the situation it may be, it gives us reproducible results, and also it produces straightforward measurement. And one more important thing is it gives more stable baseline, and also permit glass transitions to be measured very clearly in heat flux DSC mode. Now, if we look at the above graph, like when a sample, let us consider an example of ice. Let us consider ice as a sample. So when ice at its, let us assume like ice is at 0 degrees Celsius. So when I start and controlled temperature program, I'm supplying heat energy. So because of which, like the reference signal, the temperature of the reference, it goes on increasing, whereas the ice starts to melt. So until the complete ice starts to melt, the ice would be at 0 degrees Celsius. So there would be a lag between the reference and sample signal. This lag, when plotted against delta t versus time, it gives me a area. Like this area is nothing but the transition enthalpy. And through this, I can find out I can find out the value of the transition, and also depending upon whether it is exothermic and endothermic, I can also measure what type of transition it is. In this manner, heat flux DSC works. Now coming into the power compensation DSC. Power compensation DSC, basically it has two furnaces, one for sample and another for reference. So two different furnaces and two different powers are given to sample and reference. So in order to maintain a constant temperature between them, like whenever a control temperature program is set, either it may be a cooling or it may be heating program. So whatever the transition taking place in the sample, we need to compensate by either increasing our input or decreasing our power input. So whatever the power change like delta P, this helps me in telling what type of transition has been taken place. And this is directly related to find out what the value of del H. Now, as said it earlier, the power is applied to or removed from the specimen furnace to compensate for the energy change in the specimen. The system is ideally maintained in thermally null state at all times. So, whatever the difference in thermal power, it is nothing but the change in heat flux del Q related to the thermal power PR. Here, in the pictorial representation, where TR represents temperature of the reference and TS represents temperature of the sample. Here PR represents how much power we are giving to the reference, and here PS represents how much power we are supplying to the sample. And the sensor used in power compensation DAC is platinum resistance thermocouple. It gives us rapid response. So let us discuss the advantages of power compensation DAC. It gives us better resolution. So when compared to heat flux DAC and power compensation DAC, a more better and sharp peak is seen in case of power compensation DAC. And faster heating and cooling rates can also be maintained in power compensation DAC. Now coming to the DAC instrument.
This is the DST instrument available in laboratory. If you zoom, we can see the crucibles in which sample and reference are shown. This is the schematic diagram of DSC. Furnace are there on the either side of sample and reference for providing heat. Sensor calculates the temperature and sends to the data recorder or computer. And atmosphere control is important, as we can't have any reactions inside crucible with the sample. These are the parts of DSC like crucibles, furnace and heat transfer disk, sensor and signal amplifier, program or computer control, data processor or recorder or gas control device. These are the parts of DSC. In crucible, these are the inert holders on which samples are placed, which is the placed in the sensor assembly. These are the designs of crucibles like open, deep open, dimmed to fit thermocouple, glass tube, flow through, etc. like that. We have to select the material based on the range and degrees Celsius. Generally, we use aluminum. If we are using range of between 0 to 500, we have to use glass or silica. If we use graphite, it will be melted. So we have to take the material based on the range and degrees Celsius. These are the materials, these are the types, and these are the purposes.
Now coming to the sample preparation. Whatever the instrument it may be, sample preparation plays an important role. So sample preparation is important because if the sample preparation is gone wrong, the results what we are expecting would be also wrong. So it is really important and we need to discuss a lot on this. Now coming to the sample preparation, a good thermal contact and a low resistance between sensor and sample is essential. The samples used for DAC instrument are usually crystalline solid, powdered solid, liquids and solutions, but not gases. You might arise to a question like why not gases? The reason behind this is because, as we all know, the thermal conductivity of gases is very low. So it is difficult to find out the temperature when we have a controlled temperature program, and also in gases we don't have many transition taking place. So that's the reason. Now coming to the crystalline and powdered samples, excessive grinding should not be takes place. Like when a crystalline sample, if we want to measure, like if we want to find out the thermal properties, or if we want to find out the properties of the crystalline sample, we need to grind the sample. But this doesn't mean that we need to grind it excessively so that it destroys the crystallinity and allow reaction to take place. So gentle grinding should be take place. Otherwise, excessive grinding may lead to so many problems. Like for example, if we consider grinding of copper sulfate pentahydrate may cause formation of basic sulfate, and excessive grinding of explosive mixtures can produce violent reaction. So grinding should be done in a gentle manner. Now, coming to the sample of powders having low density and fibers, it is difficult to retain within the sample pan prior to sealing because fibers they won't align at a particular position in the crucible. So what we do is nothing but take a small piece of thin foil which is having the same metal as made of crucible and place it into the center of the thin foil and then fold over them to contain the sample into smaller bowl. Then put this capsule into the crucible and flatten before sealing the crucible. Now, what to do if the sample is a thin film? Just cut it in the shape of disc of radius just less than the crucible and put that in the crucible and punch it with a sharp punch and do the DSC. Now, what to do in case of liquids? In case of liquids, like if we consider liquids of involatile liquids, these are introduced into the crucible with the help of a calibrated syringe or micropipette or dropper. Care must be taken that the liquid does not spread onto the edges due to surface tension. And also, it is recommended the liquid mixture to be mixed before loading into the pan for better results to be obtained. And also, we need to make sure that droplets, if formed, they may get separately within the pan for some time. So we need to make sure that there shouldn't be any droplets within the crucible. And how to deal in case of viscous liquids? Simply take the viscous liquids with the help of a spatula and flatten against the bottom of the pan using a rod with a flat end and seal it and then do the experiment. Now coming to the sampling part. Initially, first of all, let's discuss about the whatever the picture shown in this slide. Basically, as you can see, the picture contains microbalance, which is used for measuring weight, and crucible box, which is very much required for sampling, and a crucible press. So initially, what we are doing is we will be taking a suitable crucible with a lid, and we will be weighing that. As you can see in the first line, they have mentioned that it is pierced with holes. This is because to identify, like as I mentioned it earlier, there were sample crucible and reference crucible. So like we would be to identify them, we would be piercing one crucible with one hole and the other with two holes, so that we can easily identify which one is reference and which one is the sample one. Now, these both lid and crucible are weighed in microbalance and they are noted down. Whatever the values microbalance gives, they are taken down. Now we are if the sample is powdered, we will be taking around 10 mg, or if the sample is liquid sample, we will be taking around 30 microliters, and then we will be again weighing that using microbalance. Now we need to close the crucible with lid, so we'll be doing cold pressing using crucible press, which is shown in the figure. Now, what all I have discussed, it is shown it here. Like now, initially lid is being pierced with needle, and they have been made holes, and the crucible with sample and lid is weighed in microbalance, and the sample with crucible is about to cold press, and the crucible is cold pressed. In this manner, the lid is fixed on the crucible. Now coming to the sensor. Here, thermocouples are being used to identify the temperatures in the sample and reference. So thermocouples and platinum resistance thermocouples are being used. Whatever the choice of temperature sensor, it depends completely on the need of the experimenter. and also the resistance to chemical attack, the temperature range, and the mechanical stability must be considered in addition to the thermometric sensitivity. Sensitivity is an important term which need to be discussed when we talk about the sensors. Now, coming to the sensors, like I have mentioned it earlier, there are thermocouples and there is platinum resistant sensor. In thermocouples, there are several types of sensors like Cu constant, which is having a range of minus 100 to 400 degrees Celsius, chromal aluminum having a range of 0 to 1000 degrees Celsius, platinum 10%, ruhenium. There are many these types of thermocouples. Usually, would be using a thermocouple of chromal and aluminum. If we recollect heat flux DSC, in heat flux DSC they have used they are using chromal and aluminum thermocouple. Whereas in power compensation DSC they are using platinum type RTD having a range of 0 to 1600 degrees Celsius. Now, recollecting one point from power compensation DSC, the time constant of power compensation DSC is small because the furnaces are smaller and have a faster response, which makes them suitable for very rapid reactions. One thing I want to say is that one advantage of platinum resistant sensor is that it gives me because of low time constant, it gives me a rapid results. Like it gives me very instant values compared to thermocouples. But comparing the sensitivity, both are having a low value. So, how to solve this problem? We can solve this problem with the help of thermopile. What is thermopile? It is nothing but it is an electronic device which converts thermal energy into electrical energy. It is composed of several thermocouples connected usually in series or less commonly in parallel. The basic principle on which it works is thermoelectric effect. Like basically, it generates a voltage when dissimilar metals are exposed to a temperature difference. And as you can see from the figure, this is one thermocouple on which another thermocouple is being placed, and in this manner, thermopile is being formed. Around 130 thermocouples, when placed in this manner, they form a thermopile. And the figure is of multi-star ceramic sensor, which is having a good sensitivity and is also having a low time constant. Now, coming to the types of transitions.
So till now we have discussed about the working of instrument and the working principle. So as discussed earlier, the main reason behind using this differential scanning calorimetry is observe different types of transitions. So mainly the transitions are divided into two types, exothermic transitions and endothermic transitions. Exothermic transitions are the transitions in those the release of heat is observed, whereas endothermic transitions are the transitions in which heat is observed. Some of the examples for exothermic transitions are crystallization, oxidation, combustion, fermentation, and decomposition. Whereas coming to endothermic, melting, sublimation, evaporation, glass transition, and so on. So this is a schematic diagram of the DSC curve. In the DSC curve, initially the sample which is under observation is at very high temperature, and we start the process with cooling scan. When we cool the, so as you can see at below, the cooling scan starts at high temperature and it is taken to a low temperature. From that low temperature, the heating scan starts, and with a certain heating rate, the material is heated to a temperature below its thermal degradation. So as you can see here, in cooling scan, we can observe the crystallization curve, and in heating scan, you can observe glass transition, step change, and cold crystallization curve and crystalline melting curve. Now let's see how cooling happens in the DSC. So this cooling happens in a initial. This cooling used to happen by fitting a fan or blower over the assembly. This fan will cool the whole assembly, and hence this process is employed. But the main disadvantage of this process is that here we can bring the temperature down to 40 degrees Celsius itself. If the process requires the temperature less than 40 degrees, then it's not possible. So this arrangement is later replaced with an arrangement where the furnace and whole sensor unit is kept in a refrigerated space, and this space is kept in a and this is kept in a refrigerated space where the temperature can further decrease down to minus 20 degrees Celsius. but still sometimes in some cases in cooling curve we need to decrease temperature further than that. So that new process came into evaluation, and that is the process that currently uses is usage of coolant. So this coolant is passed through the casing of the furnace in such a way that while traveling it takes out the heat from the sample and also reference, and also the parts and the heated thing will be gone out of the casing. So most widely used coolant is liquid nitrogen, because this liquid nitrogen is chosen because it is mostly available and very cheap, and also comparatively it has more CP value. So in using this liquid nitrogen arrangement, we can further decrease the temperature to minus 170 degrees Celsius. And also after taking the heat from the gas, this heat is sent to the heat exchanger, and there the heat is reused. So there is no loss of energy also. So let's see how the heat cooling arrangement occurs. So yeah, this is the cooling arrangement with DSC sample, where liquid nitrogen is taken through into the furnace of the DSC unit. As you can see, after taking out the heat, it goes into the heater where the heat is transferred and dry nitrogen is taken back, and it is again cooled, converted to liquid form and used again. So this is the DSC sample. So let's see some of the transitions and their importance. Yeah. So coming to the transitions, one of the main important transition that we use most widely in DSC is glass transition temperature, and this glass transition temperature is defined by TG. So this glass transition temperature is the temperature where the material changes its state from hard and brittle to viscous and rubbery material. And this glass transition temperature is observed in the heating scan curve. And this glass transition temperature depends upon the chemical structure, extent of polymer branching, and also cross linking. And as shown earlier in the schematic diagram, this glass transition temperature is an endothermic enthalpy change. Let's see the glass transition curve. Yeah, so this is the glass transition, and TIG is the point where glass transition starts at exact point, and this is defined as onset temperature. And TMG is the point where glass transition happens half of the way, and CP change will occurs 50%. And the most of the time while denoting glass transition temperature, this TMG is used to denote. And TFG is the point where glass transition ends, and further this point we don't observe any glass transition. And this TFG is called as end temperature. And delta CP, where the point where 50% of the delta CP happens, is called the glass transition temperature. Next. Let's see about crystallization temperature. So crystallization temperature is the temperature where material starts to crystallize if any amorphous material is present, amorphous state is present in the material. So the most of the times this crystallization is observed in the cooling scan itself. But in some cases where our cooling rate is very faster, there the most of the crystallization happens in the cooling scan, but some of the crystallization remains which happens in the heating scan. And the crystallization that we observe in the heating curve is called cold crystallization. And let's see how crystallization curve occurs. Yeah, so as shown in the figure, this is the crystallization curve where the crystallization starts at a point called TIG, which is called onset temperature. And TPC is the peak temperature, and this peak temperature is defined as the crystallization temperature. And TFG is the point where crystallization stops, and later we don't find any crystallization. And the enthalpy change of the crystallization is calculated by calculating the area under this crystallization curve. And this crystallization is an exothermic change, so that's why it is upward direction. Next. So yeah, coming to the next transition, that is melting. The melting is the temperature where polymer changes its state from solid crystalline state into amorphous liquid state. After further than this melting temperature, we don't observe any more solid polymer. And unlike if you observe any metals, they have a particular certain point called melting point where the melting used to happen. But coming to the polymers have different types of monomers and also arrangement is different. So we cannot say that melting happens at a particular temperature. It happens over a range of region. So and let's see how melting curve looks. So yeah, this is the melting curve, and this, as said earlier, melting is the endothermic reaction where energy is observed. And as you can see, this TIM is the point where melting actually starts, and it is called as melting onset temperature. Whereas the TPM, the melting peak temperature, is the temperature which we used to define as melting temperature. And the TFM is the point where the melting stops, and later we don't find any substance in the solid state. And the enthalpy of change for melting is defined by calculating the area under this curve. Next.
Coming to the calibration part. Calibration is really important. Like any instrument, it doesn't give the true value. So it is equally important to find out the calibration, and it is equally important to calibrate whatever the values we get from the experimental data. So let's understand like how calibration is affected. So calibration, it is affected by the type of instrument used and the gas and its flow rate, type of the specimen pan used, its dimensions and its position, and mass of the test specimen, heating and cooling rates, type of cooling system used. Now going to the enthalpy calibration. So this calibration, like as mentioned earlier, whatever the area under the curve, it is nothing but the change in enthalpy, but it is just directly proportional. It doesn't mean that whatever the area we are getting, it's equal to the delta Hs. There will be some calibration to that. So here the value K, which is nothing but the constant, proportionality constant, this should be found out, which is nothing but a constant which is depending on temperature, and here M is the sample mass. So how to find out this value K? So to find out this value K, we would be using two substances having different transitions. Like if we know these two substances like having if we know the values of del H, and if we can find out the value of M using the microbalance, we would be getting A when we perform the experiment. So when I know A, del H and M value, so I can easily find out the value of K. So in this manner, I would be performing for two different substances at least 3 times, and a mean value is taken. Now coming to the crystallinity of the sample. So crystallinity of the sample, it is calculated from the formula Wc is equal to del Hm by del Hm naught into 100, where del Hm naught, it is the experimental heat of fusion, and del Hm naught, it is the experimental heat of fusion for 100% crystalline material. So in this manner, we can get the value of del Hm, which is the experimental heat of fusion, from the whatever the DSC experiment we have done. And we can also find out the del Hm naught value, which is available in literature, or we can also determine using DSC. Let us see like how can we determine del Hm naught using DSC. It is basically, as I said it earlier, like it is nothing but del Hm at equilibrium temperature, Tm naught, which is nothing but the melting point of a perfect infinitely large crystal, where Tm is equal to Tc. So basically it is nothing but heat of fusion for 100% crystalline material. Now to find out the value of Tm naught, basically what we are doing is nothing but we'll be taking the sample, we'll be heating it above melting point temperature, and we are cooling it to a temperature like if we cool it to like let us consider we are cooling it to a temperature T1, and we are maintaining T1 temperature constant, and we are allowing the sample to crystallize. So in this way the sample is crystallized at a particular temperature T1, and now this temperature T1, it is called isothermal crystallization temperature. Now again the sample is heated above melting point, and again it is cooled to some other temperature T2 and allowed to crystallize, and we will be getting another isothermal crystallization temperature. In this manner, if we perform several times, we will be getting a pair of data points. And if we plot the data points Tm versus Tc, we would be getting these are the data points which we would be getting from the experiment. Now, as I said it earlier, for 100% crystalline material, Tm is equal to Tc. So this is nothing but y equal to x line. So when I extrapolate these data points, they intersect y equal to x. Now whatever the corresponding y value I am getting, that is Tm naught. So I have got the value of Tm naught. Now to find out delta Hm naught. Now in DSC basically what I am doing is I am just finding out the value of del Hm. So if I plot a graph with del Hm versus crystallization temperature Tc, so when I know the value of Tm naught. So if I find out the corresponding del Hm for Tm naught, which is equal to del Hm naught. So in this manner I have got del Hm naught. So in this way, using DSC I can find out del Hm naught. Now going into the next slide.
So till now we had seen how crystallinity is calculated. Now let's see how specific heat capacity can be calculated using DSC experiment. When you see the specific heat capacity, for that we need two empty pans and a pan filled with standard reference, and the standard reference that we most times choose is sapphire, and a pan filled with specimen material. So to do the calibration first, we have to take an empty pan and a pan with the reference material. The reason why we are taking sapphire material is because we have the data of the Cp values of sapphire at different values of temperature. So as said earlier, either heat flux method or power compensation method, you will keep both the pans and you will start the process and you will observe the heat changes. Since here we have the values of Cp for the entire range of temperature, if you can see the formula here, you have the value of Cp, you have the both values of Qs, and you have the heating rate V, and the mass of the sample M is already known. And hence from the formula you can calculate the calibration constant in the first step. And later with the calibration constant value, you do the second step where a pan filled with specimen is taken and also an empty pan is taken. And the same process is repeated with these two pans, and the heat changes are calculated. So hence again in the same formula we have Q of specimen material and Q of empty pan, heating rate, mass, and calibration constant is known. Hence we will get the Cp value of our reference temperature. So specimen material. So this is the process how we calculate specific heat capacity using this process. Coming to the next slide, you can see the graphs of. So here you can see the graph of this experiment, where these dotted lines are represented by the empty pan changes, and this dotted dash line are represented for sample, and this is for sapphire. So the difference between this empty pan and the sample is taken by the Q dot sample, and the empty pan and this sapphire is taken by the delta Q of sapphire. Yeah, so let's see the different factors that affects the DSC experiment. The first factor is effect of the atmosphere. As you already got an idea that in the DSC process we are heating the sample. So hence, if during the heating process, the sample that we are taking might release the gases, and these gases, if we don't provide any space or any hole to escape, then they might be present in the process itself, and this might create back pressure and causes reactions in the sample. So we need to make sure that there is something arrangement for the reacting for emitting the gases that are released during the heating process. And as said earlier, during specimen preparation we need to be very careful while making the sample. We should not damage or deform or heat the material. If there is something wrong happened in the specimen properties, then the values that we got from the curve is not the values of the sample, it is of the deformed sample. and also purge gas. As we got an idea that in reference in crucible we are taking sample of 10 mg or less than that. So the remaining space is left itself, and if we fill it with the atmospheric air, then the oxygen present in the atmosphere might react with the material, and it can cause oxidation reactions which is not required by us. So that's why to prevent this, what we do is we fill the crucible with an inert gas, so that there won't be any reactions. But sometimes we might think that this inert mass also has some Cp value, and it might change due to the heating the temperature. To avoid that, what we are doing is we are using the preheated inert gas in such a way that there won't be any temperature gradient. And the limitation that we need to check here is that we need to use same gas for both the calibration and also the experiment. If the gas is varied, then our enthalpy change values might vary up to 60%. Coming to the next factors. Heating rate. As you can see, the heating rate has a significant effect on the results of the sample. So the heating rate that we maintain should be adequate in such a way that it provides a sufficient time for all the transitions. We might think that high heating rate might amplify small transitions also, but the problem with that is it impairs the resolution. We cannot see how it is resolute. And starting temperature. So the starting temperature that we need to take for the sample should be 50 degrees lower than the temperature range of expected transition. Suppose if we want to see for the glass transition temperature, and if the starting temperature is more than that, then the purpose is not fulfilled. So starting temperature should be 50 degrees lower than the expected transition. And also end temperature. End temperature should not be more than decomposition temperature. If decomposition happens, then sample might change its physical state also. That's why the temperature, the end temperature should be 30 degrees higher, but no decomposition should happen. And specified mass. We need to, in some cases, the mass of the sample that we are taking depends upon the type of the transition that we observe. As seen in the table, if we are observing for glass transition temperature, the specified mass should be around 10 to 20 mg, and if for melting, it should be 5 to 10 mg, and so on. Next, one of the most important factor is effect of plasticizers. As you know, in many plastics, to improve its properties, we add some plasticizers, but these plasticizers also affect the DSC curves. If we see in some cases, in most of the cases like PVC, the rigid PVC has glass transition temperature of approx 80 degrees Celsius. But after adding plasticizers, this plasticized PVC's glass transition temperature can be decreased to minus 20 degrees Celsius. So we need to make sure whatever the sample we are taking. And also water uptake. Most of the plastics that we use are polar ones, and they absorb water from the surroundings, and this water acts as plasticizers. So as discussed, these plasticizers affect the glass transition temperature, and the results that we get are not the actual results of the sample, but these are the results of the sample after water intake. So if you can see the graph, when an amorphous PA is taken, for the dry amorphous PA, the glass transition is observed at 152 degrees Celsius, whereas if we do the same process with 2.9% standard humidity, then the glass transition temperature rapidly decreases to 108 degrees Celsius, and if we further increase the humidity to 5%, then it further decreases to 86 degrees Celsius. So we need to make sure that there is no water uptake for the sample. Next, applications. So as discussed, the DSC has many applications in many fields such as food industry, pharmaceutical, biotechnological, polymer industry, fingerprinting analysis, and reaction kinetics. Let's see some of the applications in the upcoming slides. Identification of plastics. One of the most important, most widely used application of DS is in identifying plastics. So even we know that even the plastic is composed of same monomer. There are different families for the same monomer, such as PE low density, PE high density, also PA12, PA6, PA66. Since these are same monomers, all the properties of the will be mostly same. But one of the property that distinguishes them is melting temperature. So if you can calculate the melting peak temperature of the polymer sample or plastic sample, then we can distinguish the polymers are of the same family also. Next. And also nature, so as you know that most all polymers are made of monomers, and while monomers are made, there are different kinds of process where polymerization occurs in, and in some process branching is also occurring, and the branched polymers are different from the linear polymers, and these different polymers of same monomer is can also be identified using this DSC curve of melting peak temperatures. As you can see in the graph, the three curves belongs to PE graph itself, but the three graphs have three different melting temperatures, indicating that these three belongs to different types of branching. As you can see, 135 degrees high melting temperature is for high density polyethylene, and medium temperature is for linear low density polyethylene, and other is for low density polyethylene. So hence we can distinguish between these branchings also. Next. Huh. As you can see some most of the polymers are made of from single monomer. But if a polymer is made from 2 to 3 monomers, then it is called copolymer. So and also even in this copolymer also there are different types based on the arrangement of these 2 or 3 monomers. Like you can say block polymer or random polymer or graft polymer and so on. And these categories can also be distinguished using these DSC curves by melting temperatures. As you can see in the graph, polypropylene block polymer has different glass melting temperature, and homopolypropylene has different melting temperature, and random copolymer has different temperature. So these families can also be distinguished using this DSC curve. As you can see in the right curve, POM, homo POM and POM can also be distinguished using melting temperatures. Next. And in certain circumstances, we can find the plastic by calculating the crystallinity of the sample. For example, this is the curve that we observed for after taking the DSC analysis for a sample, and we want to find the water this sample is. For this, from this curve, we can deduce that the melting peak temperature is observed at 167 degrees Celsius. And from the data available with us, we can say that the melting peak temperature of 167 Celsius is observed for either polypropylene or POM. So for initially we will go with a guess that this might be polypropylene, and since as discussed earlier, the crystallinity formula is delta HM by delta HM naught, and a delta HM for the polypropylene from this curve came out to be 173, and delta HM naught for polypropylene is taken from literature, which is comes to be 207 joule per Kelvin. So if you calculate the crystallinity with these values, then the crystallinity came out to be 84%, which is very impossible in case of plastics or polymers, because in polymers the maximum crystallinity that can attain is 75% only. Hence we can rule out the option that polypropylene, and hence the remaining one is POM. So let's see for POM also. The POM, the delta HM naught value from the literature came out to be 326 degrees Celsius. With these values, if we calculate crystallinity, which it came out to be 53%. So 53% is acceptable percentage of crystallinity. Hence, we can conclude that this polymer might be POM. In this way, we can also use the crystallinity values in identifying plastics. Now, last but not least, let's see the limitations of this instrument. So one of the main limitation is that deducing the results of this DSC curve is very difficult, and it is highly dependent on the analyst experience. So more is the experienced analyst, more is the accurate result deduction. And one of the main and important limitation is that we are taking only less part of sample for sampling or for observation. So this part does not represent the whole material, entire part of the plastic material. We need to consider this point, and we need to note this point, because suppose if you are doing for a plastic sample of bucket, and you are taking a small part of bucket and doing this process of DSC. So this small particle does not represent the whole bucket, because different parts might be made from different properties and different process, and they are combined together later. So each part has different properties, and this small part cannot represent the whole property. So if you need property of different material, then you have to take different part, different sample. and that's it. And the next limitation is comes out to be, since this DSC instrument differentiates the materials based on their melting point and glass transition point. If two materials have similar melting point or glass transitions, then we cannot differentiate those materials using this DSC curve. And also, as discussed earlier in the factors affecting that, if there are more contaminations in the plastic material, then we get very inadequate or wrong results. So this machine is highly sensitive, and we need to make sure that there are no contamination, because the contamination by noise ratio is very high. That's it. Thank you guys.